Yeah, we're recording. Thanks very much.
Great, so thanks very much, Craig. So I'm going to talk about understanding subpolar North Atlantic heat content variability in the CESM large ensemble. This is work that I've been doing at Lamont Doherty Earth Observatory, and it really comes out of a project that we did with our summer intern, Scout Jan. So she's produced a couple of the figures that are shown here, and in the group of Ryan Abernathy. I'm in Brian Abernathy's group at Lamont, and also some of this analysis is made possible by code written by Julius Busecker, who's really keen on writing lots of good Python tools. So yeah. So first, I'm going to give you a bit of introduction. I'm going to talk about recent sea level variability in the subpolar North Atlantic, and I'm going to talk about some possible mechanisms that might be driving this variability. Then I'm going to talk about our new method for partitioning heat transport into heat transport by the AMOC versus heat transport by the gyres. Then I'll show you some results in ECHO V4R3. Then I'll talk a little bit about why I wanted to look at CESM and the CESM large ensemble. I'll show you some results in CESM. And then I'll give you some conclusions. So this is kind of a motivation for why we care about this. So if you look at sea surface height trends in the subpolar North Atlantic, you'll see that from altimetry between 1993 and 2004, there was an increase in sea surface height over that period. And then there was a reduction in sea surface height in the period 2005 to 2016. And in this paper, Chafik et al., they look at this trend and they compare it to the steric trend. So you can see here from the hydrographic data, there's been an increase in sea surface height from the steric sea level between 1993 and 2004, and a decrease between 2005 and 2016. So it really seems like the steric trend is what's driving this trend. So that would be the change in heat content and or the change in salinity. And so you can sort of see that in another way here. I'm going to show you this figure or versions of this figure quite a lot throughout the talk. So you can see here on the left on the left in a sort of around 1994, there was a cold, fresh, strong subpolar gyre, and that was associated with low sea surface heights. And then up in 2005, there was this warm, saline and weak subpolar gyre that's associated with higher sea surface heights. And then the sort of state of the subpolar gyre went back to its sort of cold, fresh, strong situation. And there was a reduction in the sea surface height between 2005 and 2016. And so this is really the time period I'm going to focus on for the first half of the talk. And it really seems like the large sea surface heights are associated with warm conditions, and low sea surface heights are associated with cold conditions. And so that's what we kind of are looking at. We want to look at what's driving the temperature change, because it seems like that's what's driving the sea surface height trend. And so you can see here, there are basically two explanations for variability in heat content. The heat transport could be happening due to the overturning circulation, or it could be happening due to the gyre circulation. So I'm sure you all know about this, but you can see here, this is depth, this is latitude, this is the meridional overturning circulation. So explanation one is that northward heat transport by the surface branch of the overturning circulation, which is a northward flowing branch. If you had variability in the volume transport, then you would have variability in the heat transport from the equator towards the poles, because that's really what the surface transport is doing, is it's moving heat from the equator towards the poles. And then if you look over here, this is the alternate explanation. There's the subtropical gyre, so that's northward flow on the western boundary and southward flow in the interior. And the subtropical gyre is moving heat northward in the Atlantic, and then this is the subpolar gyre. And so variability in these gyres could also be driving variable heat transport. And so, yeah, I'll go on and talk a little bit more about the different, these two different changes in heat transport from the tropics again towards the poles. So those are kind of the two competing explanations. And I'll just talk a little bit more about the sort of existing evidence for each of the two explanations. So I think the most famous paper for the first explanation, advocating for the first explanation, is Robson et al. 2016. And they look at heat transport and heat. I mean, they mostly look at just heat content and correlations between the heat content and density in the Labrador Sea, which they're using as a proxy for the overturning strength. And so what Robson et al. 2016 find is, again, that this is from a observational product. They find that temperature in the top 700 meters increased between 1990 and 2004, and then it decreased in the subpolar North Atlantic between 2005 and 2014. And they find a similar trend actually in the salinity. And so that it seems like, you know, also waters with high temperature also are coming in with high salinity and causing a similar trend in the salinity. And so you can see here, this is why they think that it's the overturning that's driving the temperature, the temperature change. So you can see here in the red line, what they've plotted is the density in the deep Labrador Sea. So they're using that as a proxy for AMOC strength. If you have large densities in the deep Labrador Sea, you might expect to have a strong AMOC, and that's what you have up here. And then later on in the time series, you have a reduction in the densities in the deep Labrador Sea, and they're saying that means that we have a weaker AMOC later on. And they find that this change in temperature actually lags the change in AMOC strength by sort of 5 to 10 years. And so they're advocating for, okay, so that just based on the correlation, it was the AMOC, the strong AMOC, brought these high temperatures and high salinities northward. And then they go further and they analyze HADGEM3, which they have set up in a sort of 300-year control run. And again, they look at correlations between the Labrador Sea temperature and salinity, and between the deep density in the Labrador Sea and the temperature and salinity in the subpolar gyre, sorry. And so what they're saying here is that the temperature in the subpolar gyre lags AMOC transport by about 5 or 10 years. And so it really seems like that is what's going on. But it's worth pointing out that these are just correlations, and it doesn't show that every time you have an increase in the AMOC, you're going to have higher temperature and salinity coming afterwards. And it doesn't really explain all of the change in temperature that we see, maybe. And so actually, this is another paper that advocates more for the gyre explanation, and it's by Pykush et al. 2017, although I have replotted several of the figures just so that it's more consistent with the rest of the talk. So yeah, so again, in ECHO V4R3, which is a data assimilating ocean model, we have an increase in the temperature between 1994 and 2004, and a decrease between 2005 and 2015. And what Pykush et al. Do is they look at the temperature or the heat content in this black box, and they do a heat budget. And so this is sort of the initial result of that heat budget. They've sort of detrended, so they can just look at the decadal variability. And they're plotting, in black, they're plotting the total heat content. So you can see the same trend that I've been talking about I'm going to be talking about for the whole talk. You have lower heat content in the black line in sort of 1995, higher in 2005, and lower in 2016. And you can see that that variability is mostly driven by this term A, and this term A is actually the advection of heat into this region. And so, yeah, you can see the gray line is really following that pattern, whereas the red line, which is the diffusion, and the yellow line, which is the surface forcing, seem to be much less important in Echo V4R3 at forcing this decadal variability that we've been seeing. And so actually, I'm not going to show you this, but if you go and look at the paper, they find that heat transport through the southern boundary of this box is really the main driving factor. So it's advection by the ocean through the southern boundary of this box. And then they decide, okay, well, we want to figure out how much of this heat transport through the southern boundary of the box is by the overturning and how much is driven by the gyre. And they use a really time-honored method for doing that, which basically says, okay, we're going to look at the zonal average of the velocity, the zonal average of the temperature. We're going to multiply the zonal average velocity by the zonal average temperature. And then we're going to take an integral over the whole area. And so, yeah, this is a cartoon of that. They take the zonal average of the velocity, they take the zonal average of the temperature, and they multiply them together. And this is the mathematical expression if you prefer the zonal average of the velocity times the zonal average of the temperature. And so, yeah, this is kind of the, I think it seemed like quite a sensible method to go forward. It's been used several times before. And so they find this heat transport by the overturning, and then they say, okay, well, the heat transport by the gyre is basically the total heat transport minus the heat transport by the overturning. They actually do a small offset that's due to some net transport that happens in this region, but I'm not really going to talk about that because it's a kind of small component. So I think here is a good place to mention that you can do any heat transport decomposition you like. And as long as each of the components is volume conserving, that's fine. And so
doesn't it, sorry to interrupt, doesn't it need to be mass conserving?
Yes, yes, I think that because I'm in a model where, yes, you're right, it should be mass conserving.
Okay, thanks.
Yeah. But yeah, as long as each component is mass conserving, then that's fine. Yeah, okay. And please do interrupt if I say anything that doesn't make sense. Okay, so he does that. He does a zonal average of the velocity and the zonal average of the temperature. And he finds that when he does that, the result is this. So the red is the total, and the orange is this, the transport by the overturning. And you can see the orange is really not what's driving the decadal variability. It's the blue line, which is the gyre, that's driving the decadal variability. So the mathematically motivated method attributes most of this heat transport variability to the gyre. And so this is kind of the state of things when I came along. And I sort of thought maybe there's a more physically motivated way that we can partition the heat transport by the AMOC from the heat transport by the gyre. And then I'm just going to show you some of these results in Echo V4R3. So this is the overturning in Echo V4R3, and we often think about the overturning in the zonal mean, right? So this is in density space, density and latitude, and this is the AMOC in Echo V4R3, or you can look at it in depth coordinates. This is depth and latitude, and this is the overturning. But in reality, right, the northward flow. Is there a question? No. Okay. The northward flow of the is really not distributed zonally across the basin. So if you look here, what I've sort of done is I've just integrated the velocity in the sort of upper portion, the northward flowing portion of the Atlantic. I've integrated it from the western boundary eastward. And so you can sort of see a sort of pseudo stream function, which shows that when the AMOC, the water that feeds the AMOC comes into the Atlantic, it sort of goes westward across the basin, and then it flows mostly up the western boundary of the Atlantic, with perhaps some excursions in the tropical gyres or maybe in the equatorial current system. But yeah, generally the AMOC is flowing up the western boundary of the Atlantic, at least until it gets up here to the subpolar gyre. And so when you do a zonal average in order to find the transport by the overturning, you're actually maybe not taking into account the variability in the full variability in temperature that you might see on the western boundary and that might be experienced by the AMOC. And so I came up with this new method of dividing up the domain. And so again, this is sort of a section, this is depth, and this is longitude. And so these are the Americas, and this is Europe. And so, like I said, mostly the overturning is flowing in a western boundary current. And so the way that I divide up the domain is into a western boundary current that's flowing northward and feeding the AMOC, and then also a bit of a western boundary current that feeds southward flow in the subtropical gyre. So this purple region, the net transport is zero. The net volume or the net mass transport through this region is zero, and then the net volume transport through this red region plus the blue region is zero. And yes, so the blue region is the return flow of the overturning rate. And so what I'm going to do is I'm going to say there's going to be this heat transport by the gyre, which is the heat transport through the purple region, and the heat transport by the overturning, which is the heat transport through the red region, plus the heat transport through the blue region. And these regions are basically divided up through two ways. First, we have an isopycnal that goes through the maximum of the AMOC. So the maximum here, this isopycnal that divides the northward flowing transport from the southward flowing transport. And then we're also going to divide in latitude this sort of top layer that flows above that isopycnal.
Could you clarify, please, the gyre, the wind-driven gyre circulations would divide up in the same way? That is, there'd be a northward moving Gulf Stream at Gulf Stream latitudes and a return flow in the interior. Okay, it wouldn't necessarily be an overturning circulation, but it would give you the same picture, let's say, in the red and purple region.
Yes, but so, right, I think the key thing is that, right, if you just had a gyre, the total volume transport above, it really relies, right, on the fact that this isopycnal is much deeper than the subtropical gyre. And so the total volume transport of the gyre all takes place above that isopycnal, and the total volume transport of the gyre is zero, right? Because I'm including in this purple region both the northward transport of the gyre and the southward transport of the gyre.
Well, actually, it's not zero. If you're looking at time variations, right, it's not constrained to be zero over years or decades.
Yeah, okay, that's probably true. I haven't thought very much about that, and I think that is something that I maybe need to think about more in the future.
Okay, we can talk about it some other time.
Okay, thank you. Okay, so this is the figure I've already shown you. using the Pye-Cush method. And in this figure, we find that the gyre explains 71% of the variance in total heat transport through the sort of 45 North section. And then we find in our new method, the gyre only explains about 14% of the variance. And in fact, most of the variance is explained by the overturning circulation. So in ECHO before, it really seems like our method shows that the AMOC is driving the heat content variations. So then I decided I wanted to look at CESM. So what is CESM? The CESM large ensemble. Basically, there's this 40-member ensemble of fully coupled CESM simulations for the period 1920 to 2100, and they're generated by doing really slight tweaks in the air temperature for the initial conditions, which are at 1920, and then running forwards from 1920. So I only look at the period between 1940 and 2005. That's a little bit because I want to eliminate sort of any initial transient effects from the different initial conditions, but also, yeah, I picked this period to be more like the historical period, and then I use the Pangaea cloud to work with this data. And so I'm really looking at this box, which of course is a slightly different box because CESM has a slightly different model grid, but it should be relatively similar. And so you can see here, I've done a similar kind of heat budget to what Pye-Cush did. I want to know what controls the heat content in this box. And that's, so the black line shows the heat content in this box between 1940 and 2005, although of course these are sort of now fictional runs because they don't actually simulate what really happened between 1940 and 2005. And so, yeah, you can see that this is the black line, which shows the heat content between 1940 and 2005. And then the orange line shows the heat content variability that's driven by heat transport through the southern boundary of this box. And then the blue line shows sort of the rest of the heat budget. So the heat transport through the northern boundary of this box plus the heat transport through the surface of the domain. And so you can see that the total heat transport, the black line, is mainly driven by the heat transport through the southern boundary of the box in the first ensemble member. But we actually find that in the third ensemble member, for example, the total heat transport is actually a product of these two things, these two other transports cancelling quite a lot. So although the total variability is driven by the heat transport through the southern edge of the domain of the box, there's actually quite a lot of compensation with the heat transport through the northern edge of the box and with the heat transport through the surface. And so this actually really shows that there are kind of like two different regimes. I don't know, I think perhaps you could argue that there's a range of regimes. And so if you look at every ensemble member, that's what I'm showing here. So these are 10 ensemble members that I picked. And then I looked at ocean heat content variance. And I looked at how much of the ocean heat content variance was explained by advection through the southern boundary. So in the case where it's 1, then all of the heat content variance is explained by heat transport through the southern boundary. But when the ocean heat content variance, when this value is more than 1, it actually means that there's cancellation between the heat transport through the southern boundary and the other parts of the heat budget. And so the heat transport through the southern boundary is actually explains significantly more of the variance than if it was just the main driver. So yeah, so you can see that those are kind of the two regimes that we have. The case where there's sort of medium heat transport through the southern boundary drives medium heat content variability, and then there's a case where strong heat transport through the southern boundary drives moderate heat content variability, and there's a lot of compensation by the other two terms. So yeah, so there are these kind of two different regimes, and now we want to understand the heat content variability in both of them. And so you can see here, this is, again, the overturning in CESM, both in depth and in density space. It looks kind of typical. The AMOC transport maximum is about 1,000 meters depth. And so I do a lot of my subsequent work in potential density space with reference to the surface. Because we're at relatively shallow depth, that should be okay. And I think it's also worth noting that the mean AMOC transport looks pretty similar between ensemble members. It doesn't seem like there's some fundamental difference in the mean transport. So I'm actually going to compare three different methods in the CSM. The two methods that I've talked about before, so the zonal heat transport, the heat transport coming from the zonal average in depth space. So I'm going to call that the mathematical method in Z space. And then this new method that I've come up with where you divide up the domain into three regions, and that's our new method. And then I have sort of an intermediate method where instead of taking your zonal average in depth space, you take the zonal average velocity and temperature in density space, and then you multiply them together. And so that's what I'm going to show. But just before that, I just wanted to talk a little bit about I star, which is this, I star, which is this location, the longitudinal location of this boundary between the red region and the purple region. And basically the median longitude of this boundary is the same across ensemble members. The location of this boundary is not super well defined. There are moments when it's really impossible to find a location that divides the western boundary from the gyre, because often there's sort of too much southward transport in this region. But really, and so that's what causes this spikiness in the location. So this is the longitude of I star versus time. And you can see most of the time, I star sits at around 32 degrees east, west, and you have these spikes. And these spikes really come from this time when this sort of method doesn't really define I star very well. But I mean, what I will say is I can take a rolling average for a longer time period, and then I star is defined at every time step, and I get the same results. And so I think that this variability, this spikiness in I star actually doesn't really affect the results that I'm getting very much. Okay, and so here are the results that I get in CSM. They're pretty similar to the results I was getting in ECHO. The mathematical method in depth space says all the variability is due to the gyre, both in the first ensemble member and in the third ensemble member. So again, red is the total, blue is the heat transport by the gyre, and so you can see, yes, the mathematical method in depth space attributes it to the gyre. The mathematical method in density space attributes this total variability sort of split between the gyre and the overturning, and then my new method attributes most of the heat content variability to variability by the overturning. And so, yeah, I mean, this is sort of like the main result. It seems like the AMOC is what's driving the heat content variability. And I'm just going to show you a couple more things that you can do with this method to dig a bit more. In order to do that, I'm going to replot this red line, which is the total heat content variability or heat transport through the southern edge of the domain. And then I'm also going to plot some versions of this orange line. So one of the things I was worried about was that actually there was some transport by the subpolar gyre going on in this region, because I'm looking at a latitude where the subpolar gyre could start to become important. And I've really assumed that it's the western boundary current is happening here, and no transport by the subpolar gyre. And so in order to look at that, I actually did I plotted, instead of the heat transport by the overturning, which was the total heat transport in the red region times the total heat transport in the blue region, I just plotted the overturning times the mean temperature over this region, and plus the mean temperature in this region, which is what I've shown mathematically here, and that's what the orange line is. And basically the main point is it really does seem to be the mean, the regional mean temperature and the regional mean velocity that's causing this the trend that we're seeing. And so I don't think that the subpolar gyre is really affecting what I'm seeing. And then another thing that I thought I could do was I could break things up a bit in time, right? I could look at the contribution to the variability by the time mean temperature times the varying velocity, and the time mean overturning times the varying temperature, and that really shows that. So yeah, that's what I've done here. This is the temperature difference between the two regions times the total overturning. The angle brackets show the time mean. So this is time mean temperature difference times time mean overturning. I've not plotted that because it's not interesting. There's no time variation. This is the time mean temperature difference times the varying overturning. And you can see that this really is what's driving the variability. So the orange line is this, and then the red line is sort of the total. And then I've just plotted the kind of the opposite, the time varying temperature difference times the mean transport. And yeah, it really seems that that's not doing very much at all. Okay, and I mean, that's pretty much true between ensemble members as well. I'm not going to talk very much about that because I'm still working on it. But yeah, it really does seem like the time varying, the time varying component of the AMOC is what's driving this heat content variability. So here are some conclusions. Just to recap, in ECHO v4, a new method finds that the overturning is what's driving the heat content variability. And in CESM, we also find that, that our new method says that overturning is what's driving the heat transport variability. So just to sort of like explain this plot, this is the proportion of heat transport that's explained by the overturning and by the gyre in both the old method and in the new method. So in the old method, the gyre was responsible, or was thought to be responsible, for a lot of the heat transport, and was, you know, you can see that there were kind of a wide range of results. So maybe it was responsible for half, and maybe it was responsible for all of the heat transport. Whereas in the new method, there's a much narrower range of results. Basically, the new method always attributes the heat transport variability to the overturning. I think I thought I'd tell you a few things I was interested in doing in the future. One of them is sort of it would be really great if I could understand why the magnitude of variability is different between the ensemble members, and sort of try to understand better the mechanisms for that, because it really seems like even though the variability is different between the ensemble members, the mechanisms all seem to be the same that I've looked at so far. I'm also interested in trying this method at different latitudes. But yeah, so that's all from me. Thanks very much for listening. Do you have any questions?
Thanks, Spencer. That was a fascinating talk. Does anybody have any, are there any questions? I see Jeff is unmuted. Give people a second. So normally does your discussion reference the Atlantic cold pool, which was some sort of like talked about in the literature?
I think that's a kind of shorter time scale thing, and certainly I have sort of I've looked a little bit at other people's work on that, but I haven't really been focusing on that kind of time scale. At least that's my understanding.
I have a quick question. So the changes in the circulation through the 90s and subsequently seem, and there's some literature to suggest that a lot of it was driven by the changes in the NAO or other things, like basically driven by the atmosphere. Obviously, there's some coupling. Does your methodology like lend itself to demonstrating that there's a stronger connection to the atmospheric circulation changes, you know, perhaps with a little bit of a lag?
I think it would be useful for that. One of the things, right, that's I think is previous methods, especially kind of the Robson method, is I like the Robson method, but you really have to have quite a long time series and do a bunch of correlations in order to sort of understand what's going on. I think that this method, it could be useful as is sort of like part of a wider tool set for looking at that. But I think the biggest advantage of it is actually that you don't need a long time series in order to look at these things in your model. You can say, okay, I only have 10 years, but according to this decomposition, the heat transport was driven by the AMOC in these 10 years, which you probably couldn't do using the Robson type correlation method. And actually several of the other methods I've looked at. Yeah, I mean, I don't know whether that answers your question, but I haven't been thinking so much along the lines of the atmosphere yet, but I think, yeah, I mean, if this method really does work, which I think it does, yeah, I think it could be sort of part of a toolkit to look at that.
Okay, thanks.
Gavin also asked in the chat if there is a paper out on this yet.
The answer to that is no. I need to start writing the paper very soon because yeah, it's starting to be there, I think.
It's a great proof. So Amy is asking a question in the chat. Is there any chance you'd like to unmute and ask the question directly, Amy? I'm happy to read it. Also.
Sorry, I was just trying to find my mute button on my iPad. Nice talk, Spencer. Thanks. This is Amy Clement chiming in from Miami. I enjoyed your talk a lot. What does it mean to you if you upping the role of the overturning compared to the gyre, compared to the previous studies, in terms of whether it's forecasting or predictions or attribution, et cetera? Any thoughts on that?
I mean, I think that, right, for me, I'm perhaps more interested in if this is different between different models, because certainly, right, my understanding is that, right, if you go and look at the AMOC variability in different models, the AMOC variability is pretty different between many of the climate models right now. And so this is kind of like maybe a first step in starting to understand, is the AMOC driving this variability in all of the models? I think because you can do exactly the same method in all the models if you use this method. You know, I think that's really where I've come at it from. In terms of sort of predictions, of course, right, if it's more AMOC driven, we expect that buoyancy is going to be more important and winds are going to be less important. But I think that that's kind of, this method isn't explicitly looking at that, it's only looking at the transport. And so, yeah, of course, the gyre is partially buoyancy driven, and the AMOC is going to respond a bit to winds, probably, especially at these sort of short timescales. So yeah, I don't think that that's necessarily what I'm looking at. It's more about like understanding maybe why the models are different. Does that answer your question?
Yeah, thanks very much. I was just going to suggest Sarah Larson, who's at NC State now, has been doing some interesting experiments with CESM, separating out the buoyancy-driven from wind-driven circulation with a tool she calls mechanical decoupling. But you might be interested in reaching out to her, because that question of where the timescales kind of shift from buoyancy to wind-driven are at least answerable, I think, in this model with that tool. So it might be an interesting complement.
Yeah, thank you.
I see Gavin has his hand raised. Did you want to ask?
Yeah, I didn't want to just jump in again anyway, but I will. So the discussion with Amy just now raises another question in my mind, which is what is this model doing with melt on Greenland as the climate is warming? My guess is that they're assuming that total mass on Greenland is the same and therefore doesn't change over time. But obviously in the real world, it is changing quite a lot. So using the model to tell us what's happening in the real world kind of leaves out the potential impact of direct freshwater changes, not advectional freshwater changes. That might be important in the real world. Like, is there any way of kind of not dancing around that? Is there any way we can be more specific?
I mean, I think probably my answer is right now no. I think the answer is this method maybe could be applied to a model that had that included. But I don't know. I mean, I'm definitely not an expert on this. I think you and Craig much more are experts in how sort of land ice affects, melt affects ocean circulation. I really don't have an answer, I think.
Yeah, no problem. There was just something that struck me.
Yeah, I think there's still some neat experiments to be done on that. I think somebody has done some experiments on this, and I thought they were inconclusive. But I'm not either an expert in the North. I need to look into that.
I mean, yeah, I think the other thing is, right, I'm really focused, or I've so far focused on the period between 1940 and 2005, so maybe this is not very important during that period, but I could look more at the sort of later period of the CESM large ensemble. And I mean, of course, there isn't that effect, but you could look at I mean, is freshwater, are the ones with more freshwater input in the North Atlantic behaving differently? I mean, you know, more non-land ice freshwater input. And maybe that would tell you something about how the land ice would affect the overturning. I don't know.
Yes, I mean, these are experiments I think we're excited to do in the future, and we can have that, have the conversation about how the Greenland melt will be impacting the gyre circulation and heat content with those experiments.
Yeah, that sounds good.
Do we have any further questions from anyone? I think not. Okie doke. Gavin is saying thank you. So thank you everyone again for joining us this morning. Thanks again, Spencer, for your really interesting talk.
Thank you, Spencer.
Thank you. Thanks for having me.
I hope everyone has a great rest of the day.
Thank you. You too.
Patrick is clapping. So I had some technical difficulties, Spencer, at the start of the talk.
Okay.
I accidentally did not record the first few slides, I'm afraid.
Okay.
Is there any chance that you would be okay with re-recording the first few slides?
Yeah.
At some point, maybe later today.
Okay. Yeah. Just, I don't know, email me and we'll set up a time.
Okay. Yeah, sorry about that. It's just the very first couple.
Okay. Great.
Okie doke.
See you then.
I'll close this down then. Thanks, everyone.
Bye.
Ciao.